Welcome to a transformative journey through the dynamic realm of Python data manipulation. In this course, we'll explore Polars, a Python library that equips you with the tools to handle data with precision, speed, and unparalleled ease. We'll dive into data ingestion, cleaning, aggregation, the management of null values, delivery of custom functions and conditional logic, and so much more. Our goal is simply to empower you to extract the maximum value from your data in the least amount of time. Join us and unleash the full potential of Polars in Python. Let's now introduce the data that we'll be working with throughout this course. The idea of this dataset is that it's supposed to be logs from your internet service provider. So that is your internet provider, your mobile phone provider. They will get logs about your internet traffic on their network. So they will log every website you go to, the amount of data you consume, where you are when you do it, and all that sort of thing. So the data that we have here is, first of all, date time. So when did you make this request for the website? User ID, so which user made the request to access a given website? The domain names of the website that they've requested to actually access. DL bytes, which is the number of download bytes, so how big was the amount of data that you downloaded from that website. UL bytes is the upload bytes, so how large was the amount of data uploaded to the server during your request. We've got the client IP, which is the IP address of the person's mobile device or PC or whatever they're using to access the website. We've got the server IP, which is the IP address of the website itself. We've got the country that they were requesting access to the website from. The transaction time in seconds, so this particular transaction took 2.33 seconds to complete. We've got the HTTP method, which is either HTTP or HTTPS, HTTPS being the secure traffic protocol. We've then got user agent, so what user agent were they using when they made this request? And finally, we have platform, so were they on Android, Linux, Windows, Mac? What were they using to request the data? So all of this is going to be read into our Polars data frame. And when we say data frame, we simply mean a frame for our data. It can have rows and columns just like this table. It's just a way to refer to tabular data in Polars and in other libraries in Python like Pandas or Apache Spark. We use this consistent terminology of data frame, which simply means rows and columns, just like you get in this spreadsheet. For this course, we are going to use Google Colab, and this is the Google Colab interface. When you first load it up, if you've not used it before, you'll likely have no previous notebooks and no previous files that it will suggest you to open. So all we need to do is press the New Notebook button. This will load the Google Colab interface for us. And this might look familiar if you've used Jupyter Notebooks before. The beauty of Google Colab is that it's entirely cloud-based and runs in your web browser. There's no need to worry about setups or installations. On the left-hand side, we have a bunch of options. The key one here for us during this course is Files. This will give us the ability to upload our own data sets to Google Colab and to start playing with that data within our Python notebooks. On that note, Colab works with notebooks. These are interactive documents. You can add code cells and write and execute Python code or text cells to explain your work. It's perfect for combining your code with documentation, hence the name a notebook. It's like documenting your code in an executable way. We can have a quick look around Colab then. So at the very top, we have a name of our notebook. So in this case, we'll call it the Cody Polars course. That notebook is now automatically saved to our Google Drive. So it's fully integrated and gives us access to our Google Drive documents. Next down here, you can see this block. This is where we would like to write code. So we might do a equals run and print a as a simple Python statement. To run the block, you can either hold the shift key and press enter, or you can press the play button here. So we said a equals 1 and print a, and it has printed 1 as we'd expect. If we want to add a new code block, we can do by pressing plus code here. And now we might want to say b is equal to hello, and then we might want to print b. So we can execute blocks one after the other, and it gives us a nice way to structure our code and have it all separated off into isolated little blocks. We can also add text blocks, and this is great for explaining your code. So I might have a new section where I'm going to talk about if statements. And then when I say that, I have a nice title. It gives me the ability to really structure my code so that now this is a very clear section of code that obviously covers if statements. And if I come to the left-hand side here, I now have a table of contents. So I have a section called if statements, and if I click there, it will immediately take me to that section. So again, it just highlights the way that it's a nice way to structure your code, keep everything nice and organized, and run Python directly in the browser. The other cool thing is that we have almost complete control over what we want to do. So on your local PC, you might write pip install pandas, for example. You can run that in Google Colab if you just prefix it with an exclamation mark. By prefixing with an exclamation mark, it will go away. It knows that's now a system command, and it will go to install the pandas library. So whatever you want to do locally with installing new libraries or working with Python or working with files, you can do exactly the same in Google Colab without managing your own environment, installing libraries, or getting Python all configured on your local PC. Of course, that also means it's device agnostic. You can access this through any device, any browser, any time. All you need to do is log into your Google account and you will have access to your code base. So that's a quick intro to Google Colab. This is what we're going to use throughout the course. We'll actually start working with it in the next video. Okay, so let's go ahead and start actually using polars and reading data into a data frame. On the left-hand side, you have this Files tab, which will open this file window. If you click the Upload button here, and then navigate and find your course_file.csv, which is attached to this course. We can see down here that that is now uploading, so it will be available to us very shortly. So if we click away from that, first thing we need to do is make sure that polars is actually installed on Google Colab. So if we just do an exclamation mark and then pip install polars, and pip is how we install Python libraries in general. So it's just the standard way of installing a Python library. So we're just saying install polars library and make it available for us. We then need to import polars into our notebook so that we can start using polars and the polars functionality. Now, we usually shorten that to PL. So we'll say import polars as PL. And that means going forwards, I can just refer to the library as PL rather than typing the entire polars word, which, it's just really a laziness thing, to be honest, but it's the standard way of doing things. So how do we actually read data into the data frame? Well, we do df, which is shortened for data frame. It's just standard notation, but you can really call that whatever you want. We then do PL, so we're saying use the polars library because we've imported that as PL. So pl.read CSV, and then we give the name of our CSV. So if we just open it to the side, we can see it has now uploaded. We've got course_file.csv. So that's what we want to reference. So within quote marks, we can do course_file.csv. Now, my particular CSV has the first row of the data is the header. So the column headings or the column names are the first row of the data. So I want to tell polars that that is the case. So we do has header is equal to true. So that says treat the first line of this data frame as the header or the column names. So we can see that that's worked. So if we do df.head and then 2, what this does is it gives us the head of the data frame, so the top bit of the data frame, and the number in the brackets is how many rows it's going to return. So in this case, it's only going to return 2 rows because we just want to see what the data looks like. We can see that we have our date time column, and it has listed it as a string. We've got user ID, which is a 64-bit integer. Domain is a string. DL bytes, 64-bit integer, and so on. So the way that it is laid out is exactly that we have our column names, the data type associated with them, and underneath you can see some of the data that we actually have in our data frame. Other things we could do is we could actually look at the bottom of the data frame. So if we particularly wanted to look at the two bottom rows of the data frame, we could do tail. So head is the very top of the data frame, tail is the very bottom of the data frame. They both work in exactly the same way in that they just select a certain number of rows to display to us. So we now have our data in a Polars data frame ready for us to use. But we probably want to understand a little bit more about our data. Like, how many rows are there? I don't know. So we can just do len of df. And in this case, the len is the length. So what is the total length or the total number of rows that I should expect to find in this data frame? And in this case, we can see that it's 100,000 rows. Excellent. But what if I also have a very wide data frame? I can't see all the columns. So we can simply type df.columns, which we should wrap in a print statement. And that will print us a list of columns within the data frame that are available for us to use. So we can see that we have a date time, user ID, domain, DL bytes, UL bytes, and so on. So all the columns that we would expect, but it gives us a nice way to print that out. And in fact, we can iterate over this list for certain functions as well, which proves to be very useful. If we want to see what data types we have, we can do df.dtypes. So that will look at all of the data types within that data frame. And so we can see that datetime is a UTF-8, which is a string. User ID is integer 64. Domain is UTF-8, and so on. So the list of columns is in exactly the same order as the list of D types. So it allows you to really start to inspect the data and understand what we've got. To understand it a little bit more, we could do df print df.shape. And what shape is going to give us is literally the shape of the data frame. So we know that there's 100,000 rows, but we also now know there's 12 columns. So again, it just gives you another way to sort of analyze the data that you've got by analyzing the shape. Something that's super useful is if we do print df.describe, then this is going to describe our data for us in quite a lot of detail. So we don't have to then go away and start analyzing it and doing a lot of exploratory data analysis ourselves. In fact, it's done a lot of it for us here. So for each column, we have the count of values. How many of those values are null? What is the mean value across all of the records in the data set, the standard deviation, the min, the max, the median, the 25th percentile, and the 75th percentile. So this gives us a really quick view of our data, a really quick understanding of our data, and enables us to really understand what we've got to work with without needing to do any of that analysis ourselves. So this is all great. It's given us a good idea about our data frame. It's given us a good idea of how we can inspect our data, understand what we've got, understand how much data is in the data frame, what columns we have, and all that sort of stuff. So if we quickly just review what we've covered there, we've learned how to import the Polars library, and we import it as PL. We can then reference it as PL throughout the entire process of developing in Polars. So here we have pl.read CSV. So we're saying using the Polars library, read the CSV. This is the file name of that CSV. And this particular attribute here says treat the first row of that CSV data as the column headings. So the first row of the CSV includes datetime, user ID, domain, DL bytes, UL bytes. So it's saying make sure that those values are the column headings of our data frame. We then know that we can use the head function to look at the top n rows. So we could do the top 20. We can change that number to be whatever we want, but it gives us the chance to look at the top block of rows. Similarly, tail enables us to look at the bottom block of rows. So we could change this number to be whatever we want, but it just gives us a way to inspect the data at either end of the data frame, which is very helpful, of course, if it is ordered. If you ordered something by date time, the head would show you the very earliest date in your data frame, and tail would show you the very latest date. So it gives you a nice way to look at either end of the data frame. We can then use len, which is checking the length of the data frame. How many rows are there? We can print the columns using df.columns, which simply provides you with a list of columns. df.dtype provides you with a list of data types for each of those columns. df.shape tells you how many rows you have and how many columns you have, better helping you to understand what data you're working with. And df describe gives you quite a nice view of your data set with counts and averages and all that sort of stuff across your field, which helps you better understand your data without doing too much data analysis. In the next video, we will look at how we use a custom schema to bring our data in. And the reason for that is that if we go and have a look at our data types, which were down here, in this case, I might not want all of these data types to be as they have been inferred by polars. For example, I might want to change an integer 64 to be a string or a floating point or whatever I may like it to be. So I might not agree with what polars has inferred the data type of the column to be, and I might want more flexibility and control myself. So we'll have a look at that. Okay, so last time we looked at how to read data into a CSV. So just to review, we said use the polars library to read the CSV. This is the file name of that CSV, and the first row of data should be considered to be the column names. Now, we saw that when we brought our data in, that it defined user ID, for example, as an integer. Now, I know as I work in the business that my user IDs are about to change. They're going to start being string values. So I want to define this field to be string so that when my new data comes in, it still accepts the data. But at the moment, polars is inferring the schema. So it's looking at the data that's already in the data frame and it's saying, what data type do I think this should be? So we need to force it to use a different schema. So we define a Python dictionary. And what I'm going to call this one is simply custom schema. And in here, we're going to define each of the fields within our data frame and the data type that we want them to be. So we have datetime as a column, and I still want that to be a UTF-8 string value. I'm quite happy with how it was inferred by polars. The next one, though, was user ID, where that was inferred by polars to be an integer. But I don't need that. I want that to be a string as well, because as I say, my data is about to change. So we'll just have user ID. And within there, we'll do pl.utf8. So we've now changed the data type for user ID. We've told it when you read this data in, it's not an integer anymore. It is a string value. So that gives us a nice amount of flexibility for when our data ultimately changes. Now I'll paste the rest in so that we don't need to sort of manually type all these out through the video. But this is how we define the entire data set. So we've said each of the fields in our data set we have defined as an item within our dictionary. Each of the values associated to them are the data types for that we expect to be in those columns. So we've got UTF-8, which is a string value. It's alphanumeric. It's like words, things that would be considered as a string. We've got integer values. We've got floating point values. And we could define other data types in there as well, which are available to us through polars. So I have now defined this custom schema. So how do I force polars to use that custom schema when it's reading our data in? Well, we can define df as we did before, which we remember just stands for data frame. It's just a shorthand way of saying this is a data frame. And we're going to use the polars library to read the CSV. And that's going to be course file.csv. We're still going to have our has header is equal to true, because it's still true that the first row of our data should be considered as the column names. But then we're going to add an additional quote that says dtypes is equal to custom schema. So it's saying, don't try and infer the data types this time. I've already told what they are, and those values are included in the custom schema. So when we do df.head and 2 to show the top 2 rows of our data frame, we can now see that user ID is a string. So previously we saw that it was an integer, and now because we've defined our custom schema, it's now defined as a string. So when my new data starts coming in, when I've got my new user ID format, that will not cause any failures. It's already inferred as a string. So that's great. So we've now managed to determine that, or we've now managed to force polars to, rather than infer or predetermine the schema or the data types that it expects to see, we've now managed to tell it that these are the data types that we expect you to infer within the data frame. Okay, so we're very lucky that our current data set has no null values in it. There are no missing values in any of our columns. But we're building a repeatable pipeline. So when new data comes in new files, we don't know that it's always going to have no nulls in it. So let's look at some ways that we might try to address that situation. So the first thing is that we could filter out nulls. So if we're interested in filtering nulls in the date time column and user ID column, for example, there are a few ways we could do that. The first way is quite clunky, really. We're going to create a new data frame called df no nulls. And that is going to be a data frame comprised of the output of filtering our original data frame. So we're going to say df.filter. And what we're going to say is that we want to filter the data frame where the date time field is not null. So if we just add that as a single condition for now, we'll say df no nulls dot head 2. And that is going to say, let's go up and have a review, only provide the values where the date time field is not empty, it's not null. So this field must be populated, otherwise that record will not appear in df no nulls. So this is a single criteria that we have defined for our filter. But what we might like to do is we might like to have multiple filters. So we'll encapsulate that filter within an additional set of brackets, just for cleanness, really. So this particular criteria is, as we've just discussed, that date time must not be null. We can then, after that, put an ampersand, and we can create a new criteria. And this is going to be in addition to. So we're saying date time must be null, and also user ID must not be null. Is not null. So let's just check what we think that's going to do. So we're going to say we want to filter our data frame. The first bit of criteria is this, that date time is not null. The second bit of criteria is this, that user ID is not null. And here we've put an ampersand, which means and. So user ID must not be null and date time must not be null. If one is null and the other isn't, then that's fine. It will appear in df no nulls. In this case, we're saying both of those criteria must be true. If we wanted to make it an or, so filter where date time is null or user ID is null, we could change that out for a pipe, which means or is just a vertical line. But in this case, we'll leave it as the ampersand and we'll click run on that. So now we've got our new data frame, and we can guarantee that both the date time and user ID fields are not both null. Both of them, or at least one of them, has a value populated within it. So that's perfect. Now we've got other ways to deal with the same sort of problem, really. Some slightly less clunky ways. So we might want to say df no nulls 2. So it's a new data frame. We're going to call this df no nulls 2, and it's going to be df.drop nulls. And specifically, we're going to do a subset of columns. So where any of the columns within this list have a null value, we're just going to drop that record. So we're going to have date time. We've got user ID. And let's add another one just because, and we'll have domain. So this one here is telling us that we're going to drop the null values when we find a null in any of these columns. So if we now do our df no nulls 2 dot head, we can then see the output of that. So that's just another way to deal with sort of the same problem. But handling nulls is very, very important. So another way to handle nulls is you might want to just fill it with a specific value. So in this case, we're going to say df.withColumns. So this is saying we're going to actually change the columns, or we're going to add a column or remove a column or update a column. The with columns gives us the ability to do that. And we're going to say the polars column of user ID, if that is null, I want to fill that null with a particular value. And that particular value that we're going to fill it with is going to be a literal value, so an exact value, just a number or a string. So we're just going to put 22 in there. So in any case that we see user ID 22, we know that it was null. It's just it has been filled for us. Now, previously we've been looking at rewriting the data frame name and then putting .head. We don't actually have to even do that. We can just do .head and then run that. My apologies, we need to put the underscore there. So it's with underscore columns. So we now have our data. So let's just quickly review what that's done. It said whenever we find the user ID column to be null, then we should replace it with the literal value of 22. So it's simply just going to replace any missing user ID with 22. So it's just a nice way to fill it with a very specific value. But that's not really that helpful in many situations. I mean, why would you want to fill it with 22 as a static value? There's probably not very many use cases for that. So we can actually fill it with something more useful. So if we do df.withColumns again, and this time we're going to say the column I want to fill is DL bytes. And I want to fill that null value with the median value of DL bytes. And that makes much more sense, doesn't it? That if you're missing a value in DL bytes, we can sort of guess that it will be somewhere near the median. Or, you know, it gives us a way to infer a realistic value within that column. So, again, we can have a look at that. And in this case, if there were any values in here that were missing, we would then get the median value of the entire DL bytes column, which again gives us the ability to have a little bit more control or precision over the data that we fill into a null value. So we can now look at another example of filling nulls. And this one simply says, if you find any nulls in the entire data frame, irrespective of column, just fill it with a static value. So there we can just do df.fill nan, N-A-N, which is just for nulls, and we'll say 344 in this case. So if you find any nulls in any column across the entire data frame, just fill that value with 344. So that is how we're going to deal with it in this case. So we've looked at a number of things. We've looked at how we could apply a very specific filter to our data frame, where we could say when this column is not null and this column is not null, then that should form the basis of my clean data set or my new data frame. We've also looked here where we might say, look for nulls in any of these columns. And if you find them, drop the entire row. So in that case, it will say there's a null in date time, remove the entire row. We then looked at how we might fill with a specific value. So if we find a null in the user ID column, fill it with the value 22. We then looked at how we might fill the data with the median value. So in this case, we've looked at the DL bytes. And if DL bytes is empty, then we should fill that with the median of DL bytes to give us a nice realistic value. Then finally, we looked at filling the data frame anywhere that we find a null. Any null value should be replaced with 344. So actually dealing with nulls is one of the most important things when we're cleaning up our data and making it ready for analysis. So this has given you a nice grounding, hopefully, on how we might do that and different approaches to doing so. So in the previous videos, we've looked at how we read data into our data frame, how we deal with null values, but we haven't really looked at how we select only certain columns. So let's do that. So the first thing we can do is we can simply say df.select, and we can do pl.col, and in here we can do a star. And that means select all of the columns within the data frame. And that has done exactly that, and we've limited it with head. So we said pl col, and we put in there a specific column. What we might also, rather than do that, want to do is we might want to say select every column except for DL bytes. For some reason, I don't want to see DL bytes. And we can do here exclude, and within the brackets, we can do DL bytes. We can actually, of course, also add other values as well. So UL bytes. And so when we run that, we can see that we've suddenly lost these two columns here. We go from domain straight to an IP address now, whereas previously we had our DL and UL bytes. So this one is saying select every column, but not these two. So every column except those two columns. But we could also simply select specific columns as well. So we could say DL bytes, and then we'll do pl.col UL bytes. And in this case, we'll remove the exclude because, of course, we're no longer saying select everything. We're just saying select specific columns. So in this case, we always need to say polars dots. So we're saying select the polars data frame column of DL bytes and select the polars data frame column of UL bytes. We separate all the columns that we want to select with a comma. So it's very simple. It's nice syntax here that we're just saying simply select these two columns. So we've seen how we select all of the columns. We've seen how we select all of the columns except a subset of columns, so we can get rid of things that we don't really want. What else can we look at? Well, there's one other way that we can select all of the columns, which just for completeness we should cover. So we can simply just do df.select, and within that we can do pl.all. And that simply will select all of the columns within our data frame, just as the previous example we saw with the star, but in this case it's just a different syntax and worth noting in case you run into it when looking through other people's code. So that's just the very simple introduction into selecting specific columns. So if we have a very quick look through that again, let's just find the right place. Here we're saying from the data frame, select the DL bytes column and the UL bytes column. And in this case, we've limited the head to 5. In this case, we say select all of the columns from the data frame, which we do pl.all, but we could also do pl.col, and that would give us with a star in there, and the star denotes all of the columns. That will give us exactly the same output. And we also looked at how you might say select all of the columns except for where we put exclude. So select all of the columns except for DL bytes, and that would give us everything except for DL bytes. So you can see that that's missing just here. So this is quite a nice feature where we can select all the columns except, because sometimes there's just a few columns that you don't need and want to drop. And in other languages or other libraries, it can be quite painful to do so. So that's a very nice additional bit of syntax. So now we know how to select specific columns from our data frame. We know how to deal with null values. We, of course, know how to bring the data into the data frame itself. Let's talk about how we now start creating calculated columns and start getting value from our data. So what if I wanted to calculate a specific column? So for example, what if I wanted to multiply DL bytes by 5 and have that as a column in my data frame? Well, we could just do df.select, so select specific columns. As we saw last time, we're going to select the DL bytes column specifically as the first one. The next one we're going to do is we're actually going to select the pl.col of DL bytes, and then we're going to multiply that by 5. So we're just simply taking the DL bytes column, we're going to multiply it by 5. Note that this is within its own brackets to make it very clear that this is a calculation. PL col DL bytes times 5 is all encapsulated within its own brackets. And outside of the brackets, we can set an alias. And the alias is the field name. So it's like in SQL where you might say select something or select a field name as, and then you provide it a new name. It's very similar here. So we might want to call this one calculated field. The final thing we're going to do is just run the head operation to get the first number of records. So let's just run through this and make sure we're very happy with what it's doing. So we're selecting specific columns from our data frame. The first column is DL bytes. The second column is DL bytes multiplied by 5. And as I say, this particular calculation is encapsulated within its own brackets. And that means that we can really see that this is a calculation and all of these things belong together. Once our calculation has been completed, we use .alias, and .alias gives the field a name. So we can see here, this is called calculated. If I want to change the name to something else, we can suddenly see that that changes in the table. So it just gives us a way to make sure that that column is identifiable when it comes out the other side. So that's really useful for doing sort of these static calculations. But can we do multiple of these in one go? So let's try that. We'll take this as a copy and we'll spread things out onto multiple lines because it just makes it much, much more readable. So we've already got this, which we understand. We've selected our DL bytes. We've then taken DL bytes times 5. We've given it an alias, which will now change to calculated DL bytes. I also want to calculate UL bytes multiplied by 5, and I want it to be in the same table. So we can simply copy this, stick it below, and now change this to UL bytes. So we now have 3 columns in our data frame. We have DL bytes, we have the calculated DL bytes column, and we have the calculated UL bytes column. So this just demonstrates that we can include multiple calculated fields within one select statement. But note that each calculated field is encapsulated within its own brackets. So the PL col DL bytes is in its own brackets. The PL col UL bytes is in its own brackets. It makes it very clear, tidies everything up, and makes it all encapsulated so that we know that all of that calculation belongs together. Each of them has an alias of calculated UL bytes and DL bytes. And when we run the data frame, we can now see we've got our DL bytes column, our calculated DL bytes, and our calculated UL bytes. Of course, if we want to validate the data, we probably want to have the UL bytes column in there as well. To do that, we simply take exactly the same syntax here and change that to UL bytes. So now we're selecting the DL bytes column, the UL bytes column, the calculated DL bytes column, and the calculated UL bytes column. So we can validate that yes, these numbers do look like they are 5 times the original, which is great. So the other thing that we might want to do is we might want to start looking at rounding this data, because when you're doing a multiplication, it's not really a problem. But if we take this particular statement and I were to change that to divided by 5, we would find that I've left a special character there. We now see that UL bytes has a decimal place. If we change it to 5.7, for example, suddenly that decimal place becomes very large. So when we define it by 5, actually, it doesn't look too bad. It's only 1 decimal place. But if we were to divide it by a different value, that would become very difficult to read. So what do we want to do? We want to round that to 2 decimal places. And to do that, we simply have to define that we'll cast it, first of all, as a float. So we're going to tell polars that the value that we expect as a result of this calculation is going to be a floating point value. The original DL bytes and UL bytes were integer values, so we're just confirming that this is going to be a floating point. Once we've confirmed it's going to be a floating point, we can just simply use the round function of 2. So when we now run this, it forces it to 2 decimal places. So let's have a particular view of this. Let's run through this. So we're going to say we want the UL bytes column. We want to divide it by 5.7. Once we've done that, we know that it's going to be a floating point number. So we want to cast that number as floating point, just to make sure 100% that Polars knows that this is a floating point number. We can see down here that it has defined it as such. Now that that's been defined as floating point, we want to round that to 2 decimal places. And that means 2 decimal places. We could change it to 3 and it would lengthen it to 3. We could change it to 1 as well. So we can change that to be whatever we want based on the level of precision that we need for our work. So that just gives us the ability to round it to any number of decimal places. Finally, we just assign the alias to that to say that this field should be called calculated UL bytes, and that gets reflected here in the table. So that's a quick introduction to calculated fields. It shows us how we can calculate a field based on a multiplication, division, whatever it might be, how we can then cast the value of that field to a different data type, and how we can then deal with that data type. So in the case of floating points, we can round that to 1 decimal place, 3 decimal places, whatever it might be, and then we can assign an alias to it so that the output table is useful and usable and has a name that we can really use. So now we're going to start doing some really interesting stuff with our data. We want some conditional things put into our data frame. So we might want to say when the DL bytes column is over 500,000, we will consider that to be a large transaction. In all other situations, we consider it to be small. And so that is a when statement, a case statement, whatever you might like to call it. So let's have a look at how we do that. So we're going to do, as we always do, df.select. So we're going to select specific fields. In this case, we're going to do pl.col and we're going to do dl bytes. So this is the field that we're going to be working with. So I'm going to select the dl bytes column. I then want to do a when statement. So when the pl.col of dl bytes, so when the dl bytes value is greater than 500,000, then we should do something. So on the next line, we'll just indent in to make it nice and readable. We'll do then, and then we're going to actually use this lip function again. So we're going to assign a very specific value, and that is large. So we've said when the value of DL bytes column is greater than 500,000, we're going to set the value as large. Otherwise, so else or in all other situations, we're going to set the value to be the literal value of small. So then we simply want to assign an alias to this. Ooh, put that in the wrong place there. It's alias, and we're going to do this as our when statement test. And then we can do our dot head as we always would. So let's have a quick look before we run this. So we're doing a select from our data frame. That data frame is going to select the DL bytes column, and we're going to include that because it's going to enable us to actually check between the two fields, large or small, whether this condition has worked. We can then do a when statement. So when that DL bytes column is over 500,000, then print the value or set the value of the field to be large. Otherwise, set the value of the field to be small, and then we're going to give that column a name, which is when statement test. So when we run that, is this greater than 500,000? Yes, so it's set as large. Is this greater than 500,000? No, so set it as small. Is this? Yes, it's greater, so it's large. This is smaller, so it's small, and this is larger, so it's large. So our statement has worked correctly. It has taken the DL bytes column, and it said when it meets the condition that DL bytes is a greater value than 500,000, then we're going to print in the column the word large. Otherwise, we're going to print the word small, and we're going to give that column a name, and that name is going to be called when statement test. So that's the introduction to when statements. We're going to go through a few more in the following videos, but that's just a way that we can apply conditions to the values within our fields. Different example of a when statement. Here we've done some numerical comparisons to say is the value greater than or less than a certain value, and we provided a string as a response. In this example, we're going to check if a string is equal to a certain value, and we're going to apply a Boolean true or false as a response. So we're going to do our df select as we always do. So we're going to select, and in this case, let's use country. So we're going to do pl.col, and that is going to be the country column. So we're selecting from our PL data frame the column of country. We then say when that country value is equal to England, then we want to do something. And what we want to do is then return the literal value of true, and otherwise return the literal value of false. We then finally want to set an alias of is it England, which will give us the column name. So if we just move that, we have moved a bracket there. Let's always be mindful of bracket positioning. So we've selected a column of country. We've then said when that country is equal to England, return true, otherwise return false, and make that an is it England to be the column name. So if we look at head of this newly defined data frame, we can now see, is it England? Yes, it's true. Is it England? No, and it is printed false. No, it's printed false. Yes, it's printed true. No, it's false, and yes, it's true. So it seems to have worked exactly as we'd hoped it to, that it has provided those true or false values. But we could do something quite cool here. We could edit this and have a countries list. And I am only interested in Scotland and Wales. So instead of when the country is equal to England, I can do when it is in countries. So when the country value is in this list of values, then provide true, else provide false. So when we run that, is England in that list of values? No, and it's returned false. Is Wales in that list of values? Yes, and it's returned true. Scotland has returned true. England has returned false, and so on. So it gives us an additional bit of flexibility there, that we might have a static lookup list. We might say, if this value is in the static lookup list, then we can apply a certain business rule, else we'll apply a different business rule to the data. So in the next video, we'll start looking at making these slightly more intricate, adding additional conditions and things to the statement. Okay, so in this video, we're going to look at making our example a little bit more complex. So we're going to follow a very similar structure to the previous example, but this time we're going to add some additional conditions. So this time, let's do something with the platforms field. So we're going to, again, make a list, and in this case, it's going to be called platforms, and inside, we're going to have Android and Linux. So these are our platforms that we're interested in. So similarly as before, we're going to do our df.select as we always do, and we're going to now work on our when statement. So the first thing is we're going to, of course, bring in the columns we're interested in. So we want platform, and we also want DL bytes. So those are the columns that we want to be looking at. So our when statement is going to say when the platform is in this list of platforms, so when the platform is equal to Android or Linux, and the DL bytes is greater than 5,000, then we're going to print 1, else we're going to print 0. So the first thing to do is our pl.when. And we'll add a load of tabs here to make it really clear what we're doing. So inside the when statement, we have two conditions. One is that the platform must be in the list of platforms, and the other is that DL bytes must be greater than 5,000. Each of those conditions will be encapsulated in its own bracket, and it will have an ampersand for and in between. So essentially we end up with this. We're going to have within the when statement condition 1 and condition 2. So condition 1 is going to be the pl.col of platform, and then we're going to have our is in platforms. So that's our first condition. So the platform column must be in here, and if it is, we'll do something. If it's not, we'll do something else. But that's our first condition. Then we have the and sign and our second condition. So our second condition is going to be pl.col, and in this case it's DL bytes, and we're just going to simply say is over 5,000. So we have our two conditions. This condition is encapsulated within its own brackets, and this condition is also encapsulated within its own brackets. We can remove some of the spaces now to tidy it up, but the point of adding all those spaces in the first place was to really demonstrate that this is its own condition and we've encapsulated it. This is its own condition and we've encapsulated it. And that all sits within this when statement. So we just remove some of these now just to make it nice and readable. So when the platform is in the platforms list, so it's either Android or Linux, and DL bytes is greater than 5,000, then we're going to do something. So we're going to do then, we're going to have the literal result of 1. So it's simply going to be 1, and otherwise we're going to just do 0. So it's going to return a 0. And the final thing we need to do is, of course, set our alias. So our alias is going to be platform when, and then we'll do our head of 5 rows. So when we run that, we now get 11110. So Android, is it Android and is it greater than 5,000? Yes, so it's 1. Is it in the list of Android or Linux? Yes. Is it greater than 5,000? Yes, so it's 1. So the condition has worked as we expected, that both this condition and this condition are true, and when they are both true, we print 1. And here we can see we've got Windows, which is not in the platforms list. So even though the DL bytes is greater than 5,000, we still get a 0 because it does not meet both conditions. So just to run through this line one more time, because I think this is somewhere that people get a little bit stuck because there are just so many brackets. But we're saying the when statement has its own bracket. This is our condition or conditions that all live within these when statement brackets. We then have condition 1, which is within its own brackets, and that is saying that when the column platform is within this list, so when the value in platform is either Android or Linux, then that condition is met. The second condition, again, is within its own set of brackets, and that is when DL bytes is greater than 5,000. So these two are the conditions. We've got the ampersand in the middle, which means we're looking for an and. We can replace that with a pipe if we so wish, which will swap the condition to be or, and that will change the results to be always 1. Why is it now always 1? Because in every condition here, DL bytes is greater than 5,000, or the platform is either Android or Linux. So it's always one of those two conditions is always true. So that's sort of an introduction into slightly more complex examples. In the next example, we're going to now look at multiple when conditions. So we can say, when this is true, do this. When this is true, do this. When this is true, do this. And otherwise, do that. So now we're going to start adding more when conditions to add more complex logic to our calculation. Okay, so now let's start making this even more complex. So now we're going to have multiple conditions where we have multiple outcomes depending on what the value is within the field. So we're going to do our df.select as always, and inside the brackets, we're going to select a number of fields. So we're going to take the UL bytes field, and we're going to take the DL bytes field as our columns. Okay, so these are our static columns. Now what we want is we want multiple conditions here. So we want to say when UL bytes is greater than X and DL bytes is greater than X, then we're going to print large. In another situation, we're going to print medium, and in all other situations, we're going to print small. So we're calculating a flag for transaction size. So it's either going to be large, medium, or small. So we can make this super simple. We can just say pl.when, and in here, as before, we're going to have two conditions, so they're going to be within their own brackets. And we're going to say when the UL bytes column is greater than 500,000, and the pl.col of DL bytes is greater than 500,000, then we're going to do something. And what we're going to do is we'll put then we want the pl.literal value of large. So that's our first criteria. We're then going to say that this is going to continue. This statement is about to continue with something else. So we put the backslash there to say the next line is a continuation of this statement. And when we get to the next line, we start again. When. And again, we're going to say when pl.col UL bytes. And in this case, we'll do is greater than 250,000 instead of 500,000. And then another condition, pl.col DL bytes is greater than 250,000. Then we're going to do something different. And in this case, we're going to say then we want the value to be pl.lit medium, because this is a medium-sized transaction. We've got our large transaction where everything has to be above 500,000 bytes. We've got medium where everything has to be above 250,000 bytes. And now we're going to say in all other situations, we want you just to print small. So we'll just do the backslash again. It's just good practice to say this is going to be the next line. And then we're going to do otherwise. We're going to reply with pl.lit, and this is going to be small. The final thing that we need to do, as always, is fit a alias to it. So this is alias, and we're going to call this transaction size. So that's our column there defined. So let's have a quick review of what this is doing. We're saying when the UL bytes column is over 500,000 and the DL bytes column is over 500,000, we are then going to print large in this field. When the UL bytes column is over 250,000 and the PL column bytes is over 250,000, then we're going to print medium. Otherwise, we're going to print small, and we're going to give the alias of transaction size. So the column is going to be called transaction size. And you can see here that we've got large, small, large, small, large. Why is that the case? Because here, although this meets the criteria for large, this one does not. So it meets the criteria for small. This one, again, meets the criteria for large, but this one does not. So our criteria is working because both of those things must be true in order to print as we expected. Now, we looked at adding these backslashes. These are not necessarily mandatory features within your code. The code will run without them. The reason I like to put backslashes is just for readability, so that when you're scrolling through the code, you can see that this is a continuation of the line above. It's a continuation of the function above. It's just a nice way to denote that that is the case. Define a user-defined function, and this is where we define a traditional Python function and we pass our data into it and we process the data using that Python function. The reason that is so important is because Python is super extensible. You've got hundreds of libraries, loads of functionality, things you can do with your data in Python. which aren't necessarily available out of the box within polars. So having the mixture of the two, being able to run your traditional Python functions on top of your polars data frame, is super useful. So let's define a function as we always would in Python. We're going to call this calculate bytes. And it's going to ingest the row of the data frame. So we're just going to put row in there. Now, because your data is not necessarily always going to be exactly as you hoped it to be, we'll just use some try and except here. So we're going to say try to set DL bytes to be the value of row. Now, what makes this confusing is that we can't actually refer to the column name here. We have to refer to the column index number. So if I just print df.head of 2, we'll see our data. Index numbers start at 0. So date time is our first column, but it's index 0. So we've got index 0, index 1, index 2, index 3, index 4, and so on. So we don't refer to them with their specific column names. We just refer to them with the index. So DL bytes is index 0, 1, 2, 3. So I want DL bytes to be 3, and I want UL bytes to be equal to, and we're just casting them as integer just to make sure that they are the data type we want them to be. And in this case, we know that UL bytes is the next column along, so that's going to be column number 4. We are then going to simply return DL bytes plus UL bytes. And the final thing we're going to do is we're going to have our except statement. So if that function doesn't work for any reason, like we've got wrong data types or anything like that, then we want to do something different. So if there's an error in our code or an error in processing the data, we want to do something different. And in this case, we're just going to return the value of 1. So if you are unable to add DL bytes and UL bytes together for any reason, just return the number 1. So that is our Python function. We now need to apply that to our polars data frame. So we're going to do df.with columns, and we're going to apply our function. So we say df.apply because we want to apply a function to the data frame of data. Our function's name is calculate underscore bytes. So we're going to apply calculate bytes. And we now need to define the return type. So we expect the value that comes out of this addition to be an integer. Why? Because we've got an integer added to another integer. So it really can't be anything else other than an integer return type. So we just do return dtype, and we're going to define that as pl.int64. So that says return the type of a 64-bit integer. We'll then just do head of 5. So when we run that, we can now see that to the very right, we have a column called apply, and it is the sum of this and this, which is great. The problem is it's called apply, which isn't really very nice. It's just what happens by default. So we can put here .rename, and we can simply rename the columns. We put them into a dictionary, and we say, I want to rename the apply column, and what I want to rename that is called total bytes. And so when we run that now, we get a total bytes column, which is just the renamed version. So let's have a quick look at that statement then, because it gets a bit confusing. We want to take our data frame with a new column. It's going to add this total bytes column. The result of that column, or what that column should be populated with, is the result of applying the calculate bytes function that we've just defined. And when we apply that function, we expect the returns data type to be of an integer 64-bit. So a 64-bit integer as the return data type. Then simply just because the field is going to be called apply, and that's not very informative, we're going to rename that field after we've done the calculation. So we're going to rename the apply field just to be called total bytes. And then we apply that and we get our total bytes column just here. So just to review end to end then, we've done a new function called calculate bytes. It ingests a row of the data frame, so it goes one row at a time and ingests that data. For each row, it's going to try to extract the DL bytes and UL bytes, and then it's going to try and return those two values added together. If for any reason our code fails or there's a problem with our data, we will get an exception. In the case that we get an exception, we just want to return the number 1 as the value into our column. We're going to apply this function to our data by simply taking our data frame and using the with columns function. So we want to add a column to our data frame. We're going to add it by applying a function to our data frame. That function is the calculate bytes function, and that function we expect to return a 64-bit integer. We then rename the column from the default apply value to the total bytes title that we see down here. So that's how we apply a Python function to our Polars data frame so that we can start to extend the capabilities of the Polars data frame to encapsulate all the cool things that Python can do. So we've seen how to do some cool stuff with a Python UDF. We took our DL bytes and UL bytes values and we just added them together as part of a Python UDF. Clearly, it's not very complex, but it gives you an example of how we could actually take a Python function and apply it to our Polars data frame. Now, we're going to just take another simple example just to reinforce the point. So we're going to define a new function, and we're going to call this make milliseconds. And again, it's going to take a row of the data frame. So for each row, we're going to apply this function. As before, we're going to use a try. So try to run this function, and as long as there's no error or no exception, then this should be what we do. We're then going to take the transaction time column. So transaction time, and if you remember, it needs to equal the index of the column. So if we go back up here, we've got date time is index 0, index 1, 2, 3, 4, 5, 6, 7, 8. So transaction time is index number 8 in our data frame. So let's just define that then. So the transaction time is index number 8. We want to calculate milliseconds from seconds, so we're just going to multiply it by 1000. So milliseconds is equal to transaction time multiplied by 1000. And then we're going to return milliseconds. So that's our function. It's simply going to take the data from the transaction time column, which is index number 8 of our data frame. It's going to multiply it by 1000, and then it's going to return the resulting value. We then, of course, need our except block to say if you run into any errors, if our data causes you issues, if you can't complete the function, then just return 1. So that's our function. Now we need to apply that function. So we're going to do df.withColumns. So we want to add a column to our data frame, and that column is going to be the result of applying a function to our data. The function we're going to apply is called make milliseconds, which is the one we've just defined up here. And the return data type is going to be a float in this case. So we'll just use float 64 as a test. So why is it going to be a float? Because if we come up here and we say 2.33 times 1000, it's, in some cases you may have longer transaction times, I don't know. So it is a possibility that it could still be a floating point number once it's multiplied. So we'll just use float as a reliable type. So we'll just do .head on this and have a look. So float64 is not a defined data type, and that's because I haven't .pl.float64. So that's a good one to catch. Always make sure that you prefix your data types with pl. Which of course is the reference to the Polars library. So in this example, we have our transaction time of 2.33, and that has been multiplied. So it's now 2330 as an output of our function. Again, we see that the name of the column is apply, which is not very nice. So we can simply, before we do anything with the data. We can rename the column, and we're just going to rename the apply column to be transaction milliseconds. And when we run that now, we get the column renamed to transaction milliseconds, and our function has worked perfectly. So if we just run through it one more time, we're defining a Python function. It's called make milliseconds. It processes each row of our data frame, and it tries to take the transaction time from index number 8 of the data frame, which is the index number of the transaction time column. Remember, the indexing starts at 0, so when you're counting across, do keep that in mind. We're then going to calculate milliseconds by taking that transaction time value and multiplying it by 1000. And if all of that has been successful, we're going to return milliseconds as the value for the column. If that isn't successful, for whatever reason it's failed, we'll return the number 1. We then are going to apply that function to our data frame. So we're going to take our df.withColumn, so we're going to have a new column in our data frame, and that column is going to be populated by applying a function to the data frame. That function is make milliseconds, and the data type that we expect that function to return is a float 64, remembering that we must prefix the data type with PL, which is the shorthand for polars. We then finally rename the field, so we're going to rename the apply field to be transaction milliseconds, and then we look at the head of the data frame so that we can see the first 5 rows. So that's another quick example of how we can apply a Python function, a user-defined function, to our polars data frame. Now let's start looking at aggregation. How can we better understand and make use of the data in our data frame? So the way we're going to do it is, let's use a couple of examples. So we'll do df.select, and we'll start by simply summing the entirety of the DL bytes column. So we just do PL, which is polars.sum, and we do DL bytes. We can then apply it with an alias, and we'll just call that total DL bytes. And then we can do, well, we don't even need to do dot head because it should just be one row. So there we go. This is the total number of bytes in our data frame. We can expand this out as much as we like. So we might now want to take a few more examples. So we'll use lots of DL bytes examples here. We can take the min, so the minimum of DL bytes across the entire column. What is the smallest value? We can take the max, so across the entire column, what is the largest value of DL bytes? We can even calculate the standard deviation by just taking std. So we can do standard deviation of DL bytes. And we could look at the median. So the median of DL bytes, we'll change the alias accordingly. We can look at the mean. And we'll take here the mean of DL bytes. Something that's quite interesting as well is we can also take the first value. So what is the first value of DL bytes in the data frame? That's probably enough examples for here, but we can see we now have lots of columns. So the total DL bytes is this very large number. The minimum DL bytes across the entire table is 271. So the smallest value on any row in the data frame is 271. The maximum value on a given row for DL bytes is this, and so on. We get our standard deviation, the median, the mean, and the first value. So that's pretty cool. It gives us a nice way to have a single row or aggregate our data frame. But what if I wanted to say, what is the total number of DL bytes for each country? So what's the total number of DL bytes for England, total number of DL bytes for Wales, and so on? With this format, you would have to filter the data frame, have a few different data frames, get different values, and it's just a bit clunky, and it's not great. So we have another option. We can define a query. So in this case, we'll just use Q. And this query, we're going to first do df.lazy. And this means that the calculation is not executed until we call the collect command. So it will look through our calculation, understand what it does, but until we actually execute the collect command, it will not actually do anything, which is different to how pandas and other libraries works. So we're then going to do .group by, and I'm going to do country. So .group by country just means for each country. So for each country, I want to run an aggregation. So we do .ag. I want to make an aggregation for each country in the dataset. So when we open the brackets, we can then do exactly what we've done above. So we can do pl.sum dl bytes, and then we can give it an alias, and we'll do sum of dl bytes. So that now has enabled us to do this. So we're going to execute this lazily. We're going to have a group by, so for each country. For each country, we're going to run an aggregation. So for each country, we're going to sum the total number of DL bytes. And the column name is going to be sum of DL bytes. We can then come right down to the bottom and we can simply do q.collect. So as I say, this now forces it to run and it forces it to give us the result. So now we have for ing, we have a certain number of bytes, so maybe there's a misspelling in the data frame somewhere. For England, this is the total bytes, Ireland, this is total bytes, and so on. So that's a nice basic aggregation. In the next video, we'll start looking at more complex aggregations and how we can have multiple aggregations, multiple columns to group by, and all that sort of thing. But right now, let's quickly review the query one last time. So the query is defined as Q, and within the brackets, we do a number of things. We just tell it it's going to be executed lazily, and that means it doesn't actually run the code until we get to this point, until we call the collect. We're going to group by country, so that says for each country, we should run an aggregation, and that's .ag. So for each country, we're going to run an aggregation, and that aggregation is a sum on the DL bytes column, and the result of that should be stored in the column called sum DL bytes. We've set an alias for that. When we do the collect, it forces it to run and it collects the results, and this is the resulting data frame. In the next video, as I say, we'll go through some more complex examples. In this video, let's start looking at building up our aggregations. So we're going to start again with our same query, which will be encapsulated in brackets. So again, we're going to do df.lazy. It's just standard practice that this is a lazily executed command. We're not going to run it until we do a collect. And then we're going to do a .group by. In this case, we're going to group by platform. So for each platform, we need to run an aggregation. So we're going to do .ag, and within these brackets, we're going to define a number of aggregations. The first is we're going to do a count. So pl.count, and that's simply going to count the number of rows. So for each platform, how many rows in our data frame are there? So how many rows is platform equal to Linux? How many rows is platform equal to Windows? And so on. So we're going to call that an alias, and we're just simply going to call that row count. That is our first aggregation. The second aggregation, let's force the typo there. Our second aggregation is going to be a sum. So we're going to take the sum of DL bytes. So for each platform, what is the total number of DL bytes? If I add together every row related to that platform, we could add an alias to that as well if we wished, but we won't do in this case. We're also going to do something new. We're going to do pl.col, and we're going to use user ID. This is a really interesting function because this essentially captures a list of every single value in that column. So for platform, for example, Linux, it will capture every single user ID associated with Linux. So where platform is equal to Linux, what was the user ID? It captures every single one in a list. The final one that we'll look at is first. So in this case, we'll do pl.first and simply take the HTTP method column. So we'll now just do q.collect as we did before, and let's have a look at what we get. So for each platform, so we've got Android, Windows, Linux, iOS, and Mac. The first one was a row count. They're all pretty similar. Android's slightly lower than the others, but broadly they're all around 3000. The total number of bytes here is very interesting. Again, it's just the sum of the number of bytes. Here is the really interesting column. So this is each of these values is a user ID. So this user ID used Android. This user ID also used Android. So it gives us a full list of every user, but compacted into one row, which we can then process as part of a Python UDF or something similar. And then HTTP method. So the very first transaction that happened on Android was HTTPS, which is interesting to know. So that is how we define our more complex query. But if we go in here, we might want to say, actually, I want to sort the output of this query. I want the very largest row count to show first. So we simply just say sort by row count, which is the alias that we've defined up here. And then we can do descending is equal to true. So that means make the largest value at the top and the smallest value at the bottom. So when we run that, we then see that the order has changed. Windows has the highest row count of 3055, iOS has the second highest of 3033, and so on. So we now have a way to order our output of our aggregation as well, which is of course very useful. So now we're going to start looking at a super useful function, and this is a rolling function. So essentially having this sliding window across our data, and at any given time it will say, over the course of the last 2 rows, 3 rows, 5 rows, whatever we determine it to be, what is the average number of DL bytes, or the min or the max, or whatever calculation we want it to be. And imagine that's really useful if you have a sales data set and you might say over the last 3 months, what is the average number of sales? So that we can start making comparisons on a quarter by quarter basis, for example. So what we want to do first of all is we want to do a sort. So df.sort by date time. And we're going to do that in descending is equal to false. We want this in ascending order. We want the very first record, the earliest point in time in the datetime column, to be the first record in our data frame. So it's all nice and pre-sorted, and when we do our rolling windows, it's always referencing the date prior to itself. So we can simply do select here, and we can start working with our data. So we might want the pl.col of date time. We'll bring that one in, and we'll also bring in the pl.col of dl bytes. So these are our columns that we can then use to refer to understand what our rolling functions are doing. So we do pl.col of dl bytes, but now we're going to say, show me the rolling max. So the over a specified window of time, what is the maximum value that we see? We're going to set the window size to be 2, and we're going to give it an alias of max. So if we now do head of 10, let's say, on the data frame, we'll look at the top 10 rows and we'll understand what's happening here. So for each row, you can see the top one is null. Why is it null? Because it's looking at the 2 rows and it's going to give you the highest value of those 2 rows. Clearly, the first row in the data frame has nothing prior to look at. So if we look on row 2, it's now looking at this row and this row. So row 1 and 2. Which one of these is the highest value? Of course, it's row 2. So it takes in the max column that value. On the next row, it's looking at this value and this value. And we're now saying, what's the maximum value? Well, actually, row 2's value is higher than row 3. So that comes down onto the max column. The next is saying between 435 and 402. And this is, of course, the higher value. So that is taken. We can do this over a bigger window to make it even clearer. So over a 5 window, where we're saying over the last 5 values, what's the highest number? And the highest number was on transaction 2. So on our 5th transaction or our 6th transaction, we are now defining that number. Why? Because of these transactions here, that is the highest number. Here, again, within that 5 transaction window, this is the highest number, and so on. So it looks over a set period of time, and it takes the maximum value within that set period, within those currently 5 windows or 5 rows of data. We can do this, again, we'll just copy it for ease, but we can do this with other functions as well. So we've got pl.col, dl bytes again, but instead we can set min, and we'll set this one to be min. We can set, what else? We've got median, and we can set, again, the alias as median. And we can do this actually for every one of our aggregate functions. So we can do median, mean, we could do standard deviation, variance, all that sort of thing. But they all work in exactly the same way, where they look at the number of specified windows or the number of specified rows in your data frame. So in this case, within a 2-row window, what's the highest number, what's the lowest number, what's the median number, and so on. So that works really nicely. It enables us to compare time periods on a rolling basis, which is absolutely perfect for time series analysis. Now let's have a look at window functions. And window functions allow us to calculate something over a given criteria or term. So we might want to say, show me, so we'll do df.select, and I want you to show me, first of all, the country column. I also want you to show me the user ID column. So what we're going to say is, I want you to tell me the total number of DL bytes for each country, and I want you to set an alias for that. So we're going to say pl.col of DL bytes. We're then going to run our aggregation of sum, and we're going to say over, and this is going to be country. So this essentially means for each country, sum the total number of DL bytes. So if we now do our .head 5 there, we can have a look here. So we have 2 rows showing England, for example, and you will note that the number in here is exactly the same. Why is that? Because they are the same country. We said for each country, sum the total number of DL bytes. And it has. It said for England, this is the total number of DL bytes. This is also England, so it should have the same value. This is Wales, ends in 796. This one is Wales and ends in 796. So it gives you a consistent value across all of them. Why is that useful? Let's have a look at an example. So if we do pl.col, and we'll just bring our DL bytes column in here as well. So what we might want to do, so what's the problem here? Column with name DL bytes has more than one occurrence, and that's because we haven't set an alias. So if we just set an alias on here, and we'll call this one window bytes, and then we run that. So we've got DL bytes, we've got window bytes. Why is having this consistent value useful? You might say, what percent of the overall number of bytes does this transaction contribute towards England's total? So we've got 872, 807. What percentage does this transaction count towards the entire sum of England bytes? And we can work that out because we've got the 2 columns. If we think about a more sort of tangible example, we might say these are our monthly sales. What percent of our overall sales for a given country does this month represent? And so we'll do a window function and say for each month, or process it over each month. Then we're going to sum the total number of sales. So it just gives us a way to bring this different level of aggregation into the same data frame. So we can do exactly the same. Again, we could have sum, min, max, average, whatever you might want to look at. So this is just another way to run aggregations where we're saying for a specific category, in this case country, so for each country, take the minimum number of bytes, the maximum, the mean, whatever it might be, and that enables us to print a different level of aggregation within the data frame so that we can make comparisons and derive insights from that data. So let's take a little bit of time to talk about filtering. We have done some filtering throughout the course, but we've not spent time specifically talking about how to filter a data frame. So it simply just means only show me the rows where something is true. So in our example, we might want to do df.filter, so apply a filter to the data frame. We've got pl.column, so on a specific column, that column is going to be HTTP method, and I want you to only show me the records where that HTTP method is equal to HTTP. So then when we take our head of 5, we can see that now the HTTP method is only HTTP. If we swap that out to HTTPS, then when we run it, it swaps it so the HTTP method only shows HTTPS traffic. So just to quickly review, we're applying a filter. We're applying that filter on this column, and the condition we want to be met is this, that it must be equal to HTTPS. We can then apply multiple filters as well. So we could do df.filter, and we're going to apply multiple filters, which again, as with all our other functions, sit within their own brackets. So we're going to here say where pl.col of platform is equal to Mac, and then outside the brackets we say and where the pl.col of country is equal to England. And then we'll just do head and select only the top 5 rows. So what is this showing us? Well, if we scroll across, the platform is always Mac and the country is always England. So we're saying apply a filter to the data frame. We've got 2 conditions in here. The first filter is to filter the platform to only be Mac. And we have the ampersand that says and. So the platform must be Mac and the country must be England. So this applies both filters. We can also use or, so we just replace that ampersand with a pipe, which is just a vertical line. When we run that, we now get a different set of values. Why do we get this? Because we've got the country is equal to England. It is. The platform is Android though. But that's okay because we've got the or sign. So either one of these conditions has to be true. The country either has to be England or the platform has to be Mac. Whereas when we had the ampersand, both had to be true. The platform had to equal Mac and the country had to equal England, and hence we got a slightly different result set. Right, so we've been through lots of functionality in this course. We've just gone through each function, demonstrated some examples of that. Now let's try and solve some challenges. So the first challenge for you to solve is that you need to find the 5 most heavy users. So to do that, we can calculate the UL bytes plus DL bytes as a total bytes column. After we've done that, we then want to order the data, or we want to sum the values of the total bytes for each user. So we're going to want to group by user and sum the total bytes. So at this point, we now know the total amount of bytes that each transaction has used. We've now summed the total number of bytes that each user has consumed. And then we want to sort the data frame by our aggregated field in descending order. Then if we simply do a head of 5, we will get the 5 top records. So to solve that problem, we're going to calculate a new field, which is going to be UL bytes plus DL bytes. We've got a total bytes field. We're then going to group by user, and the aggregation we're going to run is a sum on the total bytes field that we've just calculated. We're then going to sort that data frame by that new field in descending order. And when we take the 5 top records using head, we will then have our 5 heaviest users. The second challenge is as below. So we're going to use a window function to find the total number of UL bytes for each country. So we're going to do window function over country where we sum UL bytes. We are then going to work out the percentage of each transaction against that total. So we're going to take UL bytes and we're going to divide it by the column we've created up here. So if we have that as an alias as country bytes, then we're simply going to do this. And that will solve our problem. So for each transaction, we're going to work out the UL bytes divided by the total number of bytes for the country, and that will give us a percentage value for that transaction. So let's go away, have a go with those. In the next video, we'll revisit them and make sure that we've got the right answers. So let's have a look at the answer to the first question. That question was to find the 5 most heavy users, and we defined that as calculating UL bytes plus DL bytes and calling that total bytes. We then sum the total bytes column per user. So we're going to group by user ID and we're going to sum the total bytes. We then sort the data frame based on that total bytes field in descending order. When we take the top 5 rows, we will have the 5 heaviest users. So here's our answer. We create a new data frame called users, and that data frame is equal to this. We select the columns of user ID, download bytes, and UL bytes from our original data frame. We then do a calculation which says take the DL bytes column and add it to the UL bytes column. And that's going to create a new column, and the alias for that column is going to be total underscore bytes. So that's the column name that I want to see in the output table. We then need to group by user and sum the total bytes. So we create a new query and we say group by user ID and run an aggregation. And that aggregation is to sum the total bytes column and give it an alias of total bytes. So in this case, we have calculated total bytes up here. So it's download bytes plus upload bytes. We're now saying for each user, if you have 5 rows, 10 rows, however many rows relate to this user, sum that field for each user and give me the total number of bytes they used across all of those rows. We then sort the table by total bytes in descending order because we've said descending is equal to true. Finally, we just collect the data and look at the head of 5 rows, which is the top 5 rows. And there we have our user ID, total bytes, and these are our heaviest users. The next one we wanted to look at was to do a window function for each country and work out what percent of each country's overall transaction value each transaction represented. So if we look down here, we create a new data frame called df2. That data frame is equal to this. We select the country column, the user ID column, the UL bytes column, and then we run our window function. So here we're saying that we're going to sum the UL bytes column over country. Really, you read this the wrong way around. You say for each country, I want to sum the UL bytes column. And so that's going to give us a total number of UL bytes for each country. We then have an alias, which is the new column name, and we call that country bytes. We can then use that, so we then say select the user ID and the number of UL bytes, and when we do a calculation, and that simply says take the UL bytes value and divide it by the country bytes value, and that will give us the percent of the overall transaction volume that this particular row represents. And at the very end, we multiply it by 100 just to give it to us as a percent rather than as a decimal. We then give it an alias of percent. So we get the column name percent, and here we can see that the percentage is calculated, and they are all quite low because each individual transaction does not contribute hugely to the overall country usage. Well done on completing the course. You've demonstrated dedication, perseverance, and commitment to enhancing your data analysis skills. Your achievement is testament to your hard work and a significant step forwards to becoming a data analysis expert. By finishing this course, you've gained valuable knowledge and practical experience in data ingestion, cleaning, aggregation, and manipulation using the powerful Polars library in Python. These skills will undoubtedly serve you well for future endeavors, whether in your career, personal projects, or academic pursuits. Once again, congratulations on your accomplishment and great work.